Right. So, welcome to the third lecture in the course Software Security. In yesterday's lecture, to give a brief overview, we discussed about the various aspects of the computer system, just sort of like a revision class, and we discussed what the operating system does, the user mode and kernel mode, and then the concept of virtual memory, right? So these were the concepts that we discussed in yesterday's class. So why those were discussed is sort of once if the base is clear, once if we have these concepts at the back of our mind, it will be useful when we further discuss these software exploits and all those things. So before directly jumping into the software exploits, first of all we should understand how the um, how a code gets compiled, right? We should understand the full compilation process that's happening. Compilation process that's happening behind the screen, right? And how the binary, so your program, once you compile it, you get a binary, right? The executable. Binary executable, how is it executed in the first place? So this process we should sort of understand. So this process we should sort of understand so that we can better appreciate the software exploits, right? And uh, and throughout this compilation process, there are many steps, and in each step there is a potential for a software vulnerability, basically. So, so understanding this process is important. So to start with, right, some of these concepts might be sort of known to you already, but the usual thing is we'll just be looking practically at, take an example and look at the code, the source code, and look at the compilation process in depth. So there will be like, so most of the concepts would be known to you beforehand, but a few things you would have overlooked while you're compiling a program. You would not have known like this much in depth output is possible, right? So those things we'll be looking in this particular lecture, right? So to start with, when you want to compile any normal program, right, you will be opening the terminal and you will, so everything will be on a Linux system, whatever commands that I'm using. So that's my assumption. So when I open the terminal, you will be opening you will be using the GCC open source compiler, and say the name of the file is main.c, right? You will be using this compiler, and it will output executable. The default name would be a.out, okay? And this a.out is the binary executable, and when you want to execute it, you just do /a.out. Say this main.c is sort of like a, it has a main function, and it does some printf. It just prints some message, invokes a couple of other functions like fun1 and then fun2. It invokes a couple of other functions and it prints a message, that's it. So this message would be printed over here in the terminal. So this will be your sort of any introduction to programming class. This will be the basic two commands that you all would have learned, how to compile a program and what happens, right? But behind these two commands, there are sort of like various stages before it reaches from this main.c to this a.out. And also when you just do the simple command /a.out, there are so many steps happening behind the screens in order to execute this simple executable, this binary. So first we'll look these two commands. We'll sort of elaborate and see what are the individual steps occurring within the system behind the hoods. So that will be the agenda of today's session. So the whole process, first let's list out the process, the stages, right? The first stage is the pre-processing stage, right? The second stage is the actual compilation. The actual compilation, and followed by that we have the assembly, the assembler phase, and after that is the linking, and after this is the loading. So these are sort of the basic five phases that happens that sort of happens when we execute these two commands. First is the compilation command, and then the execution. So basically, the first four commands, right? So basically, the phases one till the fourth one up till linking, part of the linking. Okay. So all this happens within this command gcc main.c. Basically, that single command which you use it to compile a program, right? That command takes care of all these four phases together. And the final command that you do dot slash a dot out, that is taken care in this fifth phase. So that is responsible for this fifth phase, the loading phase, and also part of this linking phase. So we'll start from the first phase, was the pre-processing. So basically, when you take a program, for example, uh, let's take this main function, right? So you will have a main.c is the source file name, and you will have a function, so it will be using the printf message, right? And part of this main function, since you are using printf, you should include this stdio.h. So this basically stdio.h, like assuming everyone knows C, this stdio.h is this standard library, and it's the header file, and the printf and all these normally used functions would be defined in this standard input output header file, and this the implementation of printf would be part of that external library. And basically I'm informing the main function that I'm using this printf function, the function type as in what all arguments it expects, where it is defined, all those details you can find it in this header file, and this header file will be placed in some part known to your GCC compiler. For it will be placed in slash user slash lib or something like that. Some part this header file will be placed available to your to all the to the entire system basically. So in the pre-processing step, what happens is all the functions which are defined in this particular header file would be pulled into this main.c. So this is what happens in your pre-processing phase. So basically all the functions, whatever which is defined external, the function type. So what I mean by function type is, so the printf, you basically take one message string, so say hello world, and then %d followed by um, the value, like I want to print integer x or something, right? So this will be how the printf would be invoked. So basically the arguments that you are passing to printf is, the first argument is a string, and followed by that you are basically passing the actual variables whatever you want to print. So this is the printf function type. So if you want to add two numbers, you will define a function add, and then int a and int b, and the return type of this add function would be another integer. So the function type of this function add is basically it takes two integers and returns back the integer as a result. So this is the function type for any function. So basically how we for any variable we tell it is of whether it's an int type or a floating point, right? Similarly, for a function, the type of the function is basically the argument, the type of the arguments it takes in, and the type of the result it emits. That's the function type. So basically, in the pre-processing phase, this hash include stdio.h and all these stuff would be sort of expanded. That whole header file would be included within your main.c source code. So let's have a look at the actual output, what I mean by this. So here I have, so I'll upload all this code in the GitHub repo, so that you, along with the commands, once the lecture is over by today or tomorrow. So you can have, you can play around with the commands, right? So I have two, I have three files. So currently, there is, let me just main.c function1.c. Okay, so I have three files over here. So one is the main function main.c. So this is the highlighted code, right? So it includes the hash include stdio.h, the standard library, and we have the main function defined, which uses the printf function. It prints this message, calls function1, it prints this message and calls function2, and that's it. And similarly for fun1.c, the second source file, I don't define, I'm not, I'm sort of not including the stdio.h, but it's sort of um, just printing a message, okay? And then we have int function2 printf over here, right? So now what, let's see what I mean by the pre-processing phase. So basically when we do gcc main.c, so before I do that, let me comment out the calls to function1 and function2 for now, right? And let me compile main.c. So when you compile main.c, you get the a dot out, and when you execute, you get this message, right? So by pre-processing phase, I pass some extra parameters to, just for better understanding, right? Pass some extra parameters to the GCC compiler and pass it main.c. So basically what happens is, this command gcc e-p basically informs the compiler that you need not compile the whole, you need not compile the program into a binary. Instead, you just stop the compilation process once the pre-processing phase is over and output the results. So that's what these two parameters are used for, the flags used for the GCC compiler. So basically, at the end of the first phase, right, without the whole compilation occurring, at the end of the pre-processing phase, this is the output that we get. And if you notice over here, your main function, right, that small two lines main function which just has the two printf statements, is just this part of the code printed over here. But before that, you have all these extra lines which are sort of included as part of the source code during this pre-processing phase. So if you notice, you will have like all these are like file operations, and if you look into these things, you have so for here, over here, so you have this printf, right? So basically I am including the standard io.h, and it's pulling all these function declarations from the header file and copying it as part of the main.c source code, right? So this is what happens in the pre-processing phase. And if you include any other header file, any like custom header file or some other header file which is part of your standard library, for example network libraries or anything, those functions will also be included as part of your source code. Okay, now say I do the same for fun1.c, right? So the output of the pre-processing phase when I try to do for function 1.c, fun1.c, it is just the logic of fun1. The reason is I don't, if I look at my source code of fun1, I don't include, so even though I'm using printf, I'm not including any standard that stdio.h header files. So basically the pre-processing files looks at the source code and notices that I'm not including any of the header files, and it doesn't do anything. It just uh, passes on the code as it is to the next step, next stage, right? So this is the output of the pre-processing phase with respect to fun1.c. So notice the difference. For main.c, you have all these declarations um, inherited from the header file, whereas in fun1.c, it's just a logic which was just passed on, and the pre-processing phase has nothing to do. So apart from having these header files, you would have come across these macros like hash define symbol and then some value. For example, hash define pi and then 3.14, and if you use this pi in all the places, it will be replaced by 3.14. So all these will also be replaced as part of your pre-processing phase only, right? So this the pre-processing phase, just the first phase, this sort of basic. Okay. So once the output of this pre-processing phase, so whatever we got over here, right, this will be passed on to your compilation process, the next phase. So let's go to the, so any doubts in this pre-processing phase? Okay. So in that case, let's move on to the compilation phase. So basically your compilation phase, what happens is, given this main.c, so whatever source code you are having, right, you pass it to your compiler, and the compiler basically emits what is called as the assembly file, which is sort of uh, following some specific ISA, right? Human readable instructions. So that's what is the assembly instructions or the ISA. So basically, what the ISA means. So ISA is another important concept. So say you have Intel systems, right? You are having so many Intel chips like i7, i5, everything. But any program that you code, say any Hello World program, any Python script or anything, you can easily run it in the i5 chip in the same way. You can pass on the executable to some other Intel chip, and you don't have to recompile or anything, but it sort of executes automatically without you doing any other extra work. Despite the fact that it is a different chip altogether, it has different features, right? The um, uh, the, the abstraction that makes all this possible is the concept of ISA. So basically, ISA is sort of the full form is instruction set architecture, right? So similarly, how when you are learning any C language or any programming language, right? C or Python, you sort of follow some standards, the syntax and all those stuff, and you follow particular semantics. So if I want to do some add operations, I should do I equal to I plus y or I plus plus, like that. So these are all available as part of your C code. Similarly, um, the instruction set architecture, what it does is that it provides like a standard as in the standard set of features or instructions that the hardware, the underlying chip, right, the hardware, the processor is guaranteed to support. So this is basically the instruction set architecture. So if you take all the Intel chips, right? For example, i5, i7, i9, Xeon, any Intel chip, right? There are like so many like different chips, different variety of chips, right? So basically, uh, what is stop? Uh, okay, so basically, the different chips, everything would be following the same ISA. For Intel, it's called as the one such ISA is the x86 ISA, 64-bit x86 ISA. So this is the standard which is common in Intel nowadays, right? And Intel also supports a 32-bit ISA. So basically, the 64 and 32-bit is uh, the size of the registers it supports. So when I explained in yesterday's class that 64-bit architecture means the register size is 64 bits, right? It is part of the processor chip. So that register size denotes the architecture size basically, which architecture it supports, how many bits it supports. So 32-bit means the maximum register size is 32 bits, and any computation should you do at max it can support 32 bits at a time. So you can add two 32-bit numbers, you can multiply two 32-bit numbers, but not more than that. In a 64-bit architecture, 64-bit ISA, any addition or any multiplication you do, you can do it on two 64-bit numbers, right? So that's what 64-bit and 32-bit architecture means in layman's term. So this ISA is sort of like a standard, sort of an abstraction. So basically, to whom this ISA would be helpful is for those who write the compilers, for the compiler engineers, right? So those who write your compilers, right? Whatever you code in your C language or Python language, you cannot directly go and execute it in the hardware. It has to be converted into something which is understandable by the hardware. So what the hardware can understand, there should be some sort of standard. It cannot be different for an i5 chip or an i7 chip. It should be like a standard. So for Intel chips, the standard is this x86 ISA, and all the language compiler engineers, whoever is writing a compiler, right? Say I'm forming and developing a new language, and for example, its name is like Rocket or something. I can write a new compiler, and what I should do is I should enforce first the language syntax and all those things, and say an addition instruction within my language. For example, in C language there is this I equal to I plus 5 or something. This operation should be converted into some set of instructions which my ISA specifies, which the x86 ISA specifies. So basically in the Intel x86 ISA, there will be like 300 instructions or something which it specifies, and each instruction will have a specific task. For example, there will be an add instruction, there will be a division instruction, there will be like multiplication, all those stuff. Using all those instructions, you should convert your C program or your Python code into this format, which is understandable by the underlying hardware. And this ISA is sort of a standard, so you don't have to redo the work when you want to execute your code on some other system, right? So basically, the compilation process is converting your source code, whatever you have written in your C code, into the corresponding ISA format, right? And the assembly file is basically the ISA format, but in sort of human understandable format, right? So this is what the compilation phase is all about. So uh, this is the compilation phase. And you might ask whether Intel is the only ISA or something. No, there are like multiple ISAs. So for example, AMD and Intel both are like sort of different computers, as in chip designers and chip companies, but both of them follow the x86 ISA, right? Whereas all your ARM, in your mobile phones, right, you have these Snapdragon, Qualcomm, all those chips, right? So they will all be following what is known as the ARM ISA, right? And recently, of late, over the past 5 years, there's this famous open source ISA called RISC-V ISA, right? So these are all, and another famous one is MIPS, right? So each ISA has sort of its own advantages and disadvantages, and basically, if I want to manufacture any chip or anything, if I'm like a sort of chip designer, I I have the resources to manufacture a chip, design a chip and manufacture it. I should sort of pick one ISA such that it acts like a reference, and my chip basically should support that ISA, as in any instruction which is part of this ISA should be able to execute on my hardware, on the processor chip that I'll be manufacturing. So this ISA sort of acts like a um, as like a agreement or something between the hardware designer and the one who designs the language or the compiler. So it's basically a sort of like a standard commitment where they tell, okay, the compiler engineer will convert the C code into this ISA, and the hardware designer should ensure that whatever processor he's designing, the chip designer, they should ensure that they support all these instructions. So when they pass these instructions according to the ISA, whatever they are supporting, the execution unit in that processor should directly execute those instructions without complaining. So that's the commitment or the guarantee that they are providing via this ISA. And this ISA design itself is a separate uh, research field, right? So this sort of the things you should understand from the ISA perspective. So the compilation phase is basically converting your source code into the corresponding ISA format. So in our class, all the examples, we will be concentrating on the x86 32-bit ISA specifically, right? So basically, why 32-bit ISA is it's sort of easier to understand all the software exploits and all those stuff, and compared to 64-bit. And as a first stage, 32-bit ISA is sort of like they're prevalent, and it's a good stepping stone to understand these software exploits. And once you understand with respect to one ISA, right, it basically sort of you can easily translate the concepts what you have known, the software exploits and all those things. You can basically translate or like transfer to any other ISA. That transfer is sort of like simple. It will take just it depends on your caliber to like sort of understand the new ISA. And you might ask a question like, why there are these many different ISAs? You have Intel, you have ARM ISA, RISC-V, right? So basically each ISA has their own design philosophy. For example, in Intel x86 ISA, so in the next lecture, we will be having an assembly refresher lecture. So we'll be discussing the basic x86 32-bit ISA instructions that we would be looking at throughout the rest of the lectures, right? So we'll be having a brief look, right? But before that, over here, like why different ISAs in the first place we have over in the outside world is that, for example, in this x86 ISA, it supports different variants of add instruction. So for example, it has an add instruction which takes like two numbers and input 1 and input 2 and returns an output, right? And also it takes another um, instruction, sort of like signed addition or something, and all those stuff. So basically what the x86 ISA is common for is any complex instruction. For example, I want to do some structure access, like you have like a structure consisting of 5 different members. You want to access the third member within a structure, or some specific um, element in the array and all those stuff. They have instructions specified for all those uh, operations which your C language provides. So this x86 ISA is sort of complex, as in it supports more than like sort I guess 300 instructions or something. So those many instructions is part of this ISA, and the compiler engineer can sort of choose from these 300 instructions what best represents his source code. So for example, uh, I equal to I plus 5, you mention it in your C language source code. This can be translated into uh, different assembly instructions in various ways. So for example, they can use the add instruction, or they can use add I like. So there are different ISA instructions, and there's just not one way to translate it, there are multiple ways, right? So that's the speciality of x86 ISA, but it's sort of very complex, and the, if my hardware has to support 300 instructions, it becomes sort of difficult to design my hardware chip in order to support all these instructions. So so to prevent that, these ISA, specifically the ARM, RISC-V and NIPS, they are sort of like not the complex ones. They just support like 100 to 150 instructions, right? So basically like they just support the basic instructions. They don't have like extra complex instructions and all those stuff, and the compiler engineer should sort of use this 150 instructions to translate the C source code to within this 150 instructions, right? And each ISA have their own reasons to follow that specific design philosophy, whether it has to be complex or whether it can be sort of easy and all those things. So depending on the ISA, the way the effort you put in to design your chip also varies. So to define a RISC-V, to design a hardware chip which supports RISC-V ISA is pretty simple when compared to designing a chip which you aim to support this x86 ISA, right? So if you have been following these processor chip news and all those stuff, there are many companies like, for example, Incore Semiconductors, which is from IIT Madras Research Park, and many other companies, right? They have all succeeded in developing these hardware chips, which supports this RISC-V ISA, right? So it's sort of like difficult, but compared to x86 ISA, it's sort of like easier to support RISC-V ISA, right? So this is what happens in the compilation phase basically. So let's look at a practical example. So here I'll be using the same compiler, GCC compiler, but I'll be passing different set of options. So basically I'll be passing this option, okay? So what this option specifies is, I'm invoking the GCC compiler, but I'm instructing it by passing this -s flag and -m ASM equal to Intel flags to mention that. So basically, this -s flag is for stopping my compilation, the whole compilation phase. So this compilation is sort of like, it's a misnomer. So this specific stage is actually your compilation phase, this -s. But instead of generating your final executable, I am instructing the compiler, the GCC compiler, to stop at the compilation phase and give the output of that stage alone. So basically what it does is, if you notice the files, it has emitted an extra file called main.s, and this main.s is so this main.s is the assembly file which is sort of human readable, and it consists of all the instructions, whatever your C code was having in the main.c, it is converted into the corresponding x86 ISA. So here I have not specified 32-bit, uh, right? So GCC-S. So if I want to specify as a 32-bit, I can do it like this. So basically, I specify -m32. So the architecture, I specify it as -m32, which is 32-bit architecture, and I stop the execute the binary generation at the compilation phase. And this over here -m ASM equal to Intel is basically I'm passing an extra parameter to the to the GCC compiler to emit those ISA instructions in the main.s file in a format which is called as the Intel syntax. So we'll be looking at that later, what that syntax means. But let's just have a peek look at what this main.s looks like, right? So this is what your main.s looks like. So these are all like the various contents in your main.s. So specifically, without going into the details, right? Concentrate at this point over here, line 12. So this basically in your main.c, I have defined my main function, and it has two printf invocations, right? So I have a symbol called as the main symbol, which is defined in the assembly file main.s, and whatever comes below this main function is basically the code which has been populated, produced by my GCC compiler during this compilation phase. So these are all x86 32-bit ISA instructions, and so whatever code, so this just as two lines of code has been converted into these many instructions within my x86 during the compilation phase. It has been converted to this corresponding 32-bit ISA, right? And the other thing that you want to notice over here is my assembly file not only contains the code which I have written over here. So this two printfs, right? It not only contains just those two instructions converted, right? But also it contains this extra parameters over here. So if you notice over here, this dot lc0 and dot lc1, you notice this line. So it mentions dot string, and then it defines a string in function main1, and then again it defines a new symbol lc1. It defines a string where it's mentioned in function main2. So basically what this denotes is, in your main.c you have used some hard coded strings to print as a message, right? Those messages are also part of this assembly file, and these are sort of called as assembly directives, right? Um, what this specifies is this part over here. So uh, I just insert a line over here, right? So what this specifies is uh, from uh, so basically our assembly file is divided into multiple sections, and each section has its own meaning and significance. So this section over here, if you notice, it defines dot section RO data, means whatever is defined within this section is just a read only data, means it's sort of constant, it cannot be changed, it is sort of encoded within your source code. And if you notice in main.c, what are the two constants as part of this program is are these messages in function main1, in function main2. So these are sort of encoded within your source code, and these are constants. So these two strings are actually present within this section, read only data, RO data, and that's why I have these two strings, and I'm specifying it as a dot string. So if I'm using like an integer or something, it would have mentioned uh, 1 or something. So let's see what happens. So for example, I do int a equal to 1, a equal to a plus 2. Let's see whether it changes. So no, so a equal to 1, it sort of doesn't do it, doesn't modify. So basically, apart from this uh, thing, right? So uh, so if I specify any other string, so if I change the string or if I specify any other string, all these constants, right? These would be stored as part of this specific section called read-only data. And whatever you specify within your code, within the part of the main function. So if I add some other function, say int dummy and int I, and then I equal to I plus 5, right? If I just add like a dummy function, and if I look at what my assembly file looks like, okay, so if you notice over here, I have my read-only data section that remains the same over here, this highlighted part. But notice that I have now a main function, and if I just scroll up, there is a new symbol which is defined, which is called as dummy, right? And if you notice this specific line over here, it specifies it is the type of this symbol. So dummy is sort of a symbol, and what does it denote? It basically denotes the function. So that's what is specified in this line, dot type dummy at function. So basically dummy is a symbol name and it denotes a function, and what it denotes is this set of instructions over here it denotes. And within what section is this dummy function placed? It's placed in this section called dot text. So dot text is basically all your code sections, whatever functions, whatever instructions you're having, everything would be placed as part of your dot text section. Similarly, if you notice the main function, you will be having this thing over here. So it is present as part of the dot text section, and you are specifying that type. The compiler specifies that the type of this symbol called main is actually a function, and all the instructions starting from here to here until this region is the dot is the main function, and everything is within the section dot text, right? And say if I add any global variables like int globe equal to 55, let's see what happens, what changes, right? So if I add any global variable, sorry, right? So if I add any global variable, so it basically sort of, if you notice, I have named a global variable as GLB. So you see, the compiler has defined a new symbol called GLB over here, okay, and it's defined a new symbol, and I'm giving the type of this symbol. It's a data object, basically it's a variable, right? And over here it is placed in the section called data section. So any global variables you define, anything you define, all this would be placed as part of the section called dot data section, and all your code, everything would be placed as part of the dot text section, and any constants encoded as part of your program, right? All those would be placed in the read-only data section. So in this example, this globe data variable, I'm specifying the value 55, right? So in the data section, uh, what this highlighted section denotes is I'm having a symbol called GLB, and it is placed within my data section, and it is size of 4 bytes, right? It's an integer, so 4 bytes, and the type is the normal data object type, and the value that it should have is 55 value, and I'm specifying that as a long value. So these are all like assembly specifics, but the key points that you should look at is the type information that I'm storing, the size of the value, and the section where I am associating this GLB variable, where it is being associated to the section, and the value that I'm associating, that I'm placing within this GLB variable. So all this information is part of your assembly file, which is generated by your compiler at the end of the compilation phase. And if I want to add an extra constraint like constant GLB, so let's have constant GLB2 equal to 66, right? So if I'm adding a constant here, and if I'm compiling the source code, right? So now you have, so if you notice, this is my old GLB variable which is present in my data section, which I have retained as it is. But now I am defining a new symbol called GLB2, which is a const integer, right? If you notice, it is not stored in my data section. Instead, it is stored in this section called .ro data. So if you recall, this ro data is the section where my other strings were stored over here in function main 1, that specific string messages which were sort of hard coded, right? Those were stored in the section ro data. So similarly, my glb2 value also, I am storing it within the section ro data, and the reason is glb2, even though it's an integer, it's a variable, it's a constant variable, so it cannot be changed. So whatever value I'm specifying within my uh, 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 within glb2, right, within the source code, it cannot be changed during runtime. So for that, I'm basically specifying this glb2 variable within the section ro data, and I'm associating the value 66 to glb2, and the size is 4 bytes. The type is, I'm specifying it as object type, and if you notice over here, I'm specifying the value as like dot long. I'm specifying as in it's like an integer value. If you look at the other symbols which is in ro data, the read-only data section over here, compare this, right? Compare this with this thing. So you just copy paste over.
అవుతూనే ఉంది దీంట్లో ఎంతమంది ఉన్నారు తెలుసా 7 మంది ఉన్నారు ఆ,
Right? So basically, if you compare this contents of ro data section to this content, right, it's pretty similar. The only difference is the string, whatever I'm passing it to the main function, to this printf function, right, in function main1, I'm not giving any name to this string. So basically, I'm not doing something like uh, character array a equal to uh, this specific string. I am not doing any definition like this within my source code. I am just directly encoding my message as part of the main function and passing it directly. So the compiler, what it does is, since the user is not, the programmer is not providing any name to this string, I am specifying, the compiler itself specifies a dummy variable name called, like a symbol name called LC0 and LC1, and associates this specific message in function main1 and function main2 to those symbols LC0 and LC1, and stores it in the section read only data. And if you compare this glb2 over here, the value which is stored in glb2 is of type integer, so the compiler specifies dot long, whereas in for the constant strings, it specifies dot string as the type of the uh, value which is being stored in that symbol LC0 and LC1, right? So basically this is what happens in my compilation phase. So three things happens. So mainly what tasks happen in my compilation phase is, if we want to sort of jot down. So first it converts converts the C code into the x86 ISA, but the human readable form. Human readable form. And second, what it does is it also places uh, uh, each part of the code, data, and then any global variables or something, right, within its own section. So basically it categorizes, okay, these are all the instructions that has to be executed, these are all the data items that has to be sort of the global variables, these are all constants which should only be read only. So it categorizes your source code basically into different sections. So that's what the compilation phase does, and the output of this phase is you can use this command line argument -s to get the corresponding output of the compilation phase. So is this clear up till the compilation phase? The example that I showed in for main.c, any queries you have? Okay, so I take that as understood everything. So so once the compilation phase is over, right, the third phase is what is called as your assembly phase. So this is where what happens is whatever uh, code that my compiler emits, right? So starting from the C code, it has emitted into what is called as the handwritten assembly instruction, that is following some specific ISA, right? So handwritten as in, sorry, human understandable, human readable specifically, right? So human readable ISA format, right? And now the assembly phase. So this is your compilation phase, and now the assembly phase is converting this human readable ISA into machine readable ISA, as in machine readable encoding. So basically in zero, ones or hexadecimal format or anything, so that when I pass it to the underlying processor, it will automatically execute this instructions, right? And this part of the software, that chunk of the software that does this specific translation, is called as the assembler, right? So basically the human readable format, so whatever we have looked in this source code over here, all these specific items, right, uh, the data section, the specification, and all the instructions over here within the dummy function and the main function, all these instructions will be converted into what is the machine readable format, and this is done by the assembler. Okay, and the command for this is gcc hyphen c main.c, and what we get is something called as the main.o file. And if we just look at main.o, right, if you notice over here, it contains some garbage like non-human readable format, right? All these things over here. Um, but basically, if you notice, some things are still human readable. Basically, the two messages that we have provided, right, in function main one and function main two, those are still readable by us. But whereas all these instructions, so if you just notice, you try to open it within the editor, you get this hexadecimal encoding, right? So basically what this means is, whatever my .es file main.es contained, everything was converted into something which can be understood by the machine, and that is stored in this file main.o, and these are called as object files. And the name, specific name, are called as object files. Okay, and once this object files are done, so this is the output of the assembler, and from here you will have so if you look at the object file, it will have the main function, whatever we saw in this human readable assembly format, everything would be in a machine readable format. Okay, so these are the object file. Now one important concept is called as the ELF format. Did someone have a doubt or something? I see someone has raised your hand. Artish, do you have any specific query?
Sir, no.
Okay, right. So there is a format called ELF format, and the full form is called as executable and linker format. So basically, what we mean by the cell format is, even for this machine readable ISA, right? It not just contains. So if you notice the main.s file, right? I specified the compilation phase is where we convert the C code into set of these instructions which are respecting the standard, following the standard x86 ISA or something. But that is with respect to my code instructions, whatever instructions that I am having within the main function or dummy function. But all these extra things over here, right? This section name and this data section. So these are all like, who defined these things? Who specified that it should be defined in this way, right? Whatever data variables that you are defining, whatever constants you are defining, it has to be part of the final executable. But the Intel x86 ISA does not provide any instructions with respect to that. It just specifies instructions that it can execute, and it should be used when you're compiling. But for the data items and all those other stuff, how the binary should look like finally, right? Where should each item should be placed? Like, okay, so whatever is placed in the data section, those are my global variables. Whatever is placed in the RO data section is sort of read only. So who defines these standards? And that is called as the ELF format, or the executable and linker format. Right? So executable and linker format is a format, ELF format, which is sort of the standard it's sort of like a similar to how we have syntax and semantics for the C language, right? For all these binary files, it follows syntax and semantics, which is called as this L format, executable and linker format, right? And any machine readable form of um, once you finish the compilation and you go to this machine readable format, everything is part of this ELF format only. Everything follows this ELF format. And this will vary with system. In Linux, it's the ELF format. But in Microsoft systems, there is the format called PE format, portable executables. So they will have a separate format on how the compiler output should look like, that handwritten assembly. So the instructions all will be same, that is that x86 ISA. But how these data variables are defined, in which section they will be associated to, that directives that I mentioned right over here, dot size, dot type, all those things will sort of be specific to the will be specific to that specific format. The dot section and all those things will be specific to Microsoft's PE format. Right. So this is what happens in your assembly phase. It converts it into a machine readable code. Now if you use the file command, so file command is basically it outputs the type of that file, whether it's an mp3 or something. So if I do file on main.c, it returns this output called, it's a C source code, and it's all ASCII text, human readable. And if I do file on main.s, it returns the output. It's an assembler source for the assembler. Everything is assembly language in a human readable form, and it's also ASCII text. But now if I do it the same for main.o, you have this long output, right? And over here, if you notice, it mentions ELF 64-bit LSB. So basically, I didn't pass the -m32 flag to specify 32-bit architecture. Now I've recompiled it. Now if I see, it mentions it's an ELF 32-bit relocatable Intel 80386, the 32-bit x86 ISA version 1 not strip. So basically the format, the file object file main.o is following is called as the ELF format. It also specifies it's following the 32-bit architecture. So all the instructions are supporting this 32-bit ISA. Okay, and this will look into the next phase, relocatable, what this means, right? So this is what is your object file. Now if you, so the object file, when we had a look into the object file, everything was sort of gibberish, like nothing was in human readable format. So there is this tool called object dump. Okay, so object dump will basically sort of, what it will do is, your assembly phase will sort of convert from human readable to machine readable format, and produce this output main.o. My object dump will do the opposite. It will take this object file main.o and give my assembly file back, but not up so detailed. To some extent, it will do the reverse conversion and give my assembly file in a human readable format. So over here I have given this object dump. I am passing main.o, the object file, the self 32-bit file, and I am specifying this option called hyphen small d. So this hyphen small d basically means, so if I look at object dump commands, what all arguments it takes, if you notice over here, this specific uh, uh, flag over here, hyphen d is disassembled, which basically displays only my executable sections, that is only that main function, the dummy function, only those things it will reverse back in a human readable format and display. If I use capital D, it disassembles all the sections. So let us look at both the outputs, what it does. So object -d main dot o. So if I this is the output that we get, right, when I pass this small -d flag. So basically the first line specifies it's an ELF32 x32, sorry, 32-bit x86 ISA, and if you notice it mentions this assembly, right, this assembly of section name is .text section, that is containing all your source instructions. And if you notice, it specifies a function called dummy, right, and these are the instructions, and then it specifies a symbol called main, which is function main, and these are the instructions within function main, right, and these are all like extra things that you need not worry about now. So basically I have two functions and it specifies the instructions of these two functions, right. But now if I do object dump hyphen capital D main dot o, apart from all the apart from the dot text section, right, if I just scroll back, so I have this is the output starting from here, and if you notice I have my dot text section, that is all my code is present over here, but apart from that even my dot data section is disassembled, and if you notice within my dot data section I have my variable glb that I have specified, and if you just scroll down you have a section called .ro data section also, and within that there is the variable glb2 also specified, and also within this section itself you will have the string in function main1 in function main2, and there are other sections also which is sort of specific to the x86, sorry, to the ELF format. So we need not go into those details, but the important concept, the takeaway is my assembler sort of, when I do this compilation flag -c to the compiler, it generates a object file, it generates an object file, right, and when I pass the same to object dump, it does the reverse and it gets me a human readable format. One thing to notice is uh, if you notice over here disassembly of section eh_frame and all these stuff, right, if you notice the main.s file, if you search for eh_frame you won't have a section called eh_frame. So these extra sections were inserted by your assembler when it is uh, which is in uh, following the standard, the ELF standard, right. So all these sections, the extra sections which were inserted, frame, dot comment and all those stuff, these were all sort of inserted by the assembler when it is converting to a machine readable format, so that it has to be ready for execution on the system, right. And when I pass that file to object dump, it just disassembles everything and gives back whatever was present, right. So in the object dump there are other parameters, flags that I can pass. So for example I can pass like this, right, and so basically what this means is I don't want the disassembly output of the entire file, but I want a disassembly output, the human readable form of a particular section, specifically I want of this read only data section .ro data, and I pass it via this flag -sj followed by the section name, and the output, if you notice, it shows contents of section ro data, and it shows these contents. So it shows the contents in the hex format as well as in ASCII text value, right. So the first value it shows b is something like that, and then in function main1, in function main2, right. So if you remember, this in function main1 is the one that we sort of have those constant strings that we are passing to printf, these two strings in function main1 and main2. So these were the two strings that were present in the read-only data when we looked at the main.s assembly file over here. Yes, right. So we have these two strings, but what does this b actually denote to? So b, if you look at this corresponding hexadecimal notation, it is ASCII text, right? B, so basically it is 0x42. So if I open my Python interpreter and do 0x42, that's basically integer value 66. So if you remember my GLB2 value, which is a constant integer, is uh, given the value 66 and stored in this read-only data section, right? So that value, it's stored as 0x42, and while displaying it as ASCII text, it shows it as capital B, which is the corresponding ASCII text notation. So this is your read-only data section containing the B66 value and these two strings, right? So this is what is the assembler phase does, and when you want to look at the reverse output, this is what happens. This is the output. The reverse output will look like, right? So any doubts till now? What happens in the assembly phase and the reverse of this assembly phase? What happens? Okay, so in that case, the next phase that after once this assembly phase is over done. So just give me a second. Right. Sorry for the inconvenience. So this is the assembly phase, and once the assembly phase is over, we have the next phase, which is my linking phase. Right. So the linking phase basically, what it does is, in your libraries or in your function, you will be using many third-party library functions. So, for example, you are using this printf function, right? So the logic for printf, we are not providing that logic, but instead the logic is provided by a library called as libc library, glibc library. So this glibc library is sort of standard and is available to all the source code or all the C source code that you want to compile, and it is installed at some specific location in your system, and it can be used by everyone. And it exports these common functions like printf, network access, file open, file read, fopen, fread, fclose, all those stuff. So in my main function, in the main.c file, I have included this printf function. I'm invoking this printf function, but I don't have the source code for printf function. So basically, when I try to execute, so whatever I get from the so once my assembly phase is over, right, I pass this flag for 32-bit, and I get the main.o object file. And if I try to execute this main.o object file, it will tell permission denied, that is one. And even if I try to do it tells it cannot execute a binary because it's of the wrong format. So basically what wrong format is, if you look at the contents of the binary, so um, if you look at the object dump, so object dump of this binary, um, so what happens is, specifically if you look at, 1 second. Okay, so basically what I have done is I've added an extra flag to the GCC compiler called -g. Okay, so -g is basically I am having extra information in the object file, whatever is that is getting generated within main.o, which makes my debugging process easier. So if I find some error in my program when executing, right? So finding those will be easier when this extra debugging information is there. Okay, and what I do is now I pass a special flag called -s, which sort of checks whether the debugging information is there in the object file main.o. If yes, it will also specify, it will also generate a file, right? I'm actually storing the output from the terminal, redirecting it into a file called main.debug. You can give any name, and basically the output of this disassembly. So previously I used hyphen small d, but here I am using hyphen es, which basically adds some extra information to make reading that disassembly sort of helpful, easier. So if I look at the output of the disassembly, so previously when you had a look at the output of disassembly, it had sort of just these instructions over here, just like that. But now if you notice, it has included also the source code of your main function. So int main, int a equal to 1, printf, and then another printf, and then we have the function closing, right? So all this source code, it has sort of included it within my disassembly. And what's the logic behind this is, say for example you take this int a equal to 1, right? The corresponding assembly instruction is this specific one, move well, this specific instruction. And if you look at printf in function main one, this single operation in C code is translated into these many instructions in your assembly code, the corresponding x86 ISA code. So it contains a sub instruction, push instruction, and all those instructions. Similarly, another printf operation is converted into these set of instructions in your assembly. So this is what basically adding the debugging flag and using that hyphen s when we are disassembling the output results in this specific output. So in this one specific line we should look into is this specific line. So basically I want to invoke a function called printf, and I'm passing the string parameter in function main one, right? So if you look at line 51, so for those who don't know x86 ISA, in C code you have these function calls, right? So basically from one function you are jumping to another function. So the same is provided by the x86 ISA, and the name of that specific instruction is known as call instruction. And the call instruction, basically what it takes as an argument, right? It basically takes the address where the target function which should be invoked that address is specified as the argument to this call instruction. So basically wherever my printf function is stored, in main memory, in your virtual memory, that printf function would be stored at say 0x1000. So it should be called 0x1000 or some other location wherever my printf function is stored. So this is what my x86 assembly instruction for a function call should look like. So when you are doing this printf in function main 1, it consists of two parts when you convert it into assembly. One, I should pass this parameter in function main1 to that printf function, and then I should invoke the printf explicitly. So the first three instructions, sub, LDA and push, correspond to passing this argument to the main to the printf function from the main function, and after I pass the argument, I store the argument somewhere. I explicitly invoke this printf via this call instruction, right? So this call instruction should have the address where my printf is located. But if you notice over here, the number which is specified for the call instruction is 52, and the indexes, if you look at the left extreme, right, 47, 4a, 50, 51, 56, these are sort of starting from this location, right, starting from this here 0, 4, 5. These are basically size of each instruction, and 56 52 sort of comes between 51 and 56, right? But for fact, my printf function is not located over here, but I'm specifying the address as 52. That's where my printf function is located. This is an error because my printf is not located over here. It is located somewhere else within my library file, glibc file. So then how do we resolve this? How do we get to know where my printf function is located? So in my, once the assembly phase is over, the output consists of this call instruction. But if you look at the call instruction, we have this wrong address being specified for printf. So here where my linking phase comes into picture. So the linking phase, what it does is, it sort of gets your source code, sorry, not source code, it gets the object file, which is passed to my linker, right? And once it's passed to the linker, my linker sort of resolves all dependencies, okay, and what it generates is the final a.out executable. Okay, so basically whatever third party library you are using, standard input output library which is using printf or anything, everything my linker will have access to, and it will include those functions, that logic within my object file, within a new file where the object file main function, dummy function will be present, as well as the logic for the printf function will also be present, and all this together, it will link together, sort of it's linking everything together, all the dependencies and the object file, and the final output is what you get as the a.out executable, and this you can execute as /a.out, because now you have all the dependencies resolved and you will know where every function is present, and when you execute it will work properly. Okay, so for example, there is a utility called vdelf utility, and if I pass, if you look at the file type of the main.o, whatever is um, coming out of my assembly phase, right? I mentioned it is an L file, but yeah, you see the extra term called relocatable, it's, right? So basically, what we mean by relocatable is, if you look at the object dump of this main file, you there is just all the functions whatever you have defined within your source code, those are only present in your main.o. But the linker should actually link in all these external dependencies like printf, any functions that you are using, all that logic should also be inserted inside, right? So basically, at the assembly phase, you won't know where these functions are, one, and you also won't know where my main function, dummy function, all these data variables, everything will be placed in the memory finally. So in that virtual memory, where will each function be placed, you the assembly phase won't know, right? But my linker phase, in the linking phase, it will know where the libraries are there, and it will know where to place each of the functions which I have defined in my source code. So it basically resolves all the dependencies, and it generates a final executable which addresses specified properly with respect to the virtual memory, right? So that's why we have the type of the object file from the assembly phase as relocatable, as in my main or dummy function, I have the corresponding ELF format as in the x86 ISA format, but all those are relocatable, as in it can be placed anywhere in the virtual memory by the linking phase, by the linker. So that is what it means by relocatable, because the linker is yet to add all these third-party code, printf, and all those things, the library functions, and for that, for proper functioning, for the proper placement, my object file, whatever the assembly phase produces, should be relocatable, so that it can be sort of, you can change the layout and all those stuff, whatever optimization it can do and all those stuff it can perform, and generate this a.out executable. So that is what the linking phase denotes. So if you notice, so I'll be using now the standard command main.c, and then -o main. So basically, instead of okay, so gcc main.c -m32. So I have my a.out file. Now what I can do is I can do object dump. So I passed a debugging flag. I am doing object dump on hyphen yes a.out and storing it in a.out debug. So let's have a look at this file. So if you notice over here, it shows disassembly of section dot text. Okay, so in the previous main dot debug, if you notice disassembly of section dot text, it just showed the dummy function, main function, and a couple of other things. That's it. Whereas over here, if you notice, it has this extra function called underscore start function. And if you scroll down, there are other functions also, register tm clones and all those stuff. And if you scroll down further, you have the main function, and within main function, since I've used debugging information, right, past -g flag. Now if you notice, right, the call to printf function and the corresponding assembly instructions. The corresponding assembly instruction specifically, if you notice this line, right, it is specified call 1070 put us at plt. Okay, so basically in my previous, just looking at the disassembly of my object file, the call instruction was call 52. Basically it is calling the next location, the next instruction within the main function itself. But once I have passed through the linking phase, after the linking phase is over, now if you notice, the call instruction has changed. So instead of 52, it is calling, it should call a function which is present at this address called 1070. And if you look at what 1070 contains, it contains a function called putus at plt. So basically, this is my printf function. So this sort of optimization done, that's, we'll look later. But putus is the library, right? If you want to display anything, you will be using this function called putus. So that function's code is actually present at this location 1070. So that's what is present, is specified in this call instruction. So put us at PLT. Uh, So if you notice, both the call instructions over here, both have been changed by the linker. So that value 52 has been changed by the linker to point to the proper address where my putters, the printer function is located as part of this source code. And now when I execute dot slash a dot out, it displays properly. Because I know where my printf function is located, it can go and invoke it, it can execute the logic and finish execution, right? So this is what happens in the linking phase. So coming to the loading phase, right? So if you look at file a dot out, right, it is mentioned over here, it's an ELF32-bit, and notice it is not mentioned relocatable anywhere. So it is not mentioned relocatable. There are cases where it could be mentioned, but that's different. But over for now, it's not mentioned relocatable. So it means the addresses are sort of determined, and it specifies over here with debug info. Since I have passed -g flag, okay, and then we have this information called dynamically linked and stuff like this. So this is where your compilation phase and the linking phase gets over. And once you execute the code, right, your code sort of executes. So when you do this dot slash a dot out, this function, this ELF file sort of gets loaded by the operating system into the virtual memory. A process gets attached to the virtual memory, and then your execution begins, prints the message, and stops, returns back. So this is what happens in the loading phase. Okay. Um, so these are the 5 phases when we do these two commands, gcc main.c, and then when we try to do dot slash a dot out. There are a couple of other things that I want to mention, specifically the dynamically linked interpreter, but and also static and dynamic linking, but that will take a few more minutes, which uh, cannot be done now. So I'll explain it at the start of the next session on Friday. It will take around like 15 minutes, right? But it's important I explain it properly and not fast to fast forward that part, because that's sort of important. And multiple exploits that we'll be studying refers basically to this dynamically linking and all those concepts. So I don't want to hurry that. Uh, so we'll stop with this. So basically, this is where this is what happens in the 5 different phases. So we have starting from the pre-processing, we looked at the compilation phase, then the assembly phase, and then we looked at the assembly phase, and then we looked at the linking phase, how it resolved this printf function, how that instruction got changed and all those things, and then it finally made the executable working and we executed it. So any doubts in these phases or in any of the commands that I had used? Any doubts you have, you can post it in the Discord channel for week 1. Or yeah, I'll upload the video recordings and I'll share the link, and the code snippets also I'll upload to the GitHub repo along with these commands that I have used. So any specific doubts you have? Okay. So if not, then we will wrap up this session. We'll end this session. Thank you all for attending. We'll meet next week Friday, October. Yeah, next week Friday, which is October 13th. Right. So October 13th at 7 o'clock, 7 p.m. We will meet. Okay then. Thanks everyone. Thanks for joining. Um, and those who have not yet formed teams, please do form teams.